Welcome. We will now learn about Amazon Relational Database Service, commonly referred to as Amazon RDS. Amazon RDS is a managed relational database service that provides 6 familiar database engines that you can choose from. These database engines are Amazon Aurora, MySQL, MariaDB, Oracle, Microsoft SQL Server, and PostgreSQL. Because RDS is fully managed, it handles routine database tasks such as provisioning, patching, backup, recovery, failure detection, and repair. The basic building block of RDS is the database, known as the DB instance. The DB instance is an isolated database environment that can contain multiple user-created databases. It can be accessed with the same tools and applications that you use with a standalone database instance. When you create a database instance, you specify its class, which determines the CPU, memory, and network capacity of the server that is provisioned. RDS supports 3 types of instance classes: standard, memory optimized, and burstable performance. You also specify the instance storage type. The instance storage is an Amazon EBS volume that is allocated to the DB instance. You determine the type, performance, and size of the EBS volume. With regards to storage, RDS provides 3 types listed here. Notice that 2 are based on solid-state drives, or SSDs. There's General Purpose SSD, which is also known as GP2, Provisioned IOPS SSD, which is also known as IO1, and Magnetic. Database instance classes and instance storage types differ in performance characteristics and price, which enables you to tailor your performance and cost to the needs of your database. Because it's a fully managed service, Amazon RDS automatically creates periodic backups of a database instance. The entire instance is backed up to a storage volume snapshot during a backup window you specify. You can also specify how long to retain the backup. The first snapshot of a database instance contains the full data. The subsequent snapshots are incremental, which contain only the data that changed since the most recent snapshot. You'll also have the ability to back up a database instance manually by creating a snapshot. For more information about working with backups, search for Amazon RDS Backup and Restore in the AWS online documentation. As you can see here, the AWS CLI allows you to create an RDS snapshot. Note that the command requires you to include the DB instance identifier and the DB snapshot identifier, which is also known as the name of the snapshot. When the command is successful, the response will include information that describes the snapshot, such as the snapshot identifier and the database engine. Now here is the AWS CLI command that is used to restore from a snapshot. When the command is successful, it will return a response that includes information about the snapshot, such as the database instance identifier and the status of the snapshot restore. Be aware that after you restore a DB instance, it will not automatically be a member of the same security group as the original DB instance. If you want the same functionality as the previous DB instance, you must add it to the original security group. Here's how to copy an RDS snapshot using an AWS CLI command. Note the optional flag of copy tags, which ensures that the new copy retains all the tags of the original. When the command is successful, it will return a response that includes information about the snapshot. The information includes the status of the snapshot, which will be shown as creating. Occasionally, you must delete RDS snapshots. To do this, use the AWS CLI command. Please note that there is no confirmation response when you delete snapshots. If the command is successful, it will return a response with information about the snapshot. This information includes the status, which will be deleted. One of the main features of Amazon RDS is that you can configure a database instance with high availability using a multi-AZ deployment. This configuration automatically generates a standby copy of the database instance in another availability zone within the same VPC. After RDS makes the initial full copy, transactions are synced to the standby copy. Running a database in a multi-AZ deployment can enhance availability during planned system maintenance. It can also help protect your database against database failure and disruptions to availability zones. The diagram illustrates an RDS database instance that is configured with high availability. The primary instance runs in availability zone 1, and it serves requests from applications that run in availability zones 1 and 2. The standby replica runs in availability zone 2, and it provides data redundancy. It is synced from the primary instance. If the primary database instance fails, Amazon RDS automatically brings the standby database instance online as a new primary instance. Requests from both applications are then directed to the new primary instance. The failover happens without needing to change the application code because the requesting applications reference the database by name using the Amazon RDS Domain Name System, or DNS, endpoint. The synchronous replication means that there is no data loss. There are several ways that you can increase the capacity of your Amazon RDS installation. First, you can increase the capacity of a database server by changing its instance class, which enables you to increase the CPU and memory that are available to that instance. Just remember, when you change the instance class, there will be some downtime. This is also known as scaling vertically. Secondly, you can modify the allocated storage in order to increase storage capacity without incurring downtime. The diagram illustrates another way to increase performance. By adding read replicas to increase the performance of read-heavy database workloads, you can scale out beyond the capacity of a single database instance. For more information about scaling or RDS storage types, search for scaling your Amazon RDS instance vertically and horizontally, or RDS storage, respectively, in the AWS online documentation. Thanks for watching. We'll see you in the next video. Welcome. We will now learn about Amazon Aurora. Amazon Aurora is a fully managed relational database engine that is compatible with MySQL and PostgreSQL. It's optimized for the cloud and provides the benefits listed here. First, it's fast and available. Amazon Aurora provides up to 5 times the throughput of a standard MySQL database and 3 times the throughput of a standard PostgreSQL database. It enables you to easily scale up and down and grow storage depending on your needs. Amazon Aurora is also simple to set up. It uses familiar SQL queries. It's compatible with MySQL and PostgreSQL, so you can run your existing applications and tools without making modifications. Finally, the pay-as-you-go service model of Amazon Aurora means you only pay for the storage and I/O operations your database consumes. Amazon Aurora also has a serverless offering that provides an on-demand automatic scaling configuration. The database automatically starts up, shuts down, and scales capacity up or down based on your application's needs. With Amazon Aurora Serverless, you can run your database in the cloud without managing any database instances or clusters. For more information about the Aurora Serverless, search for it in the AWS online documentation. Amazon Aurora provides high availability by storing 6 copies of your data across 3 availability zones. You can also create up to 15 read replicas. When you create an Amazon Aurora instance, you create a database cluster. A database cluster consists of 1 or more DB instances, along with a cluster volume that manages the data for those instances. An Aurora cluster volume is a virtual database storage volume that spans multiple availability zones. Each availability zone has a copy of the DB cluster data. An Amazon Aurora DB cluster includes 2 types of DB instances. First, there's the primary instance. It supports read and write operations and performs all of the data modifications to the cluster volume. Each Aurora DB cluster has 1 primary instance. Second, there are read replicas. Read replicas only support read operations. Each Aurora DB cluster can have up to 15 Aurora replicas in addition to the primary instance. Multiple replicas distribute the read workload, and you can increase availability by locating them in separate availability zones. The diagram illustrates an Aurora DB cluster showing the relationship between the cluster volume, the primary instance, and the Aurora replicas. For more information about Amazon Aurora DB clusters, search for Aurora Overview in the AWS online documentation. Thanks for watching. See you in the next video.
Hi, I'm Jane Wither from Amazon Web Services. Today we're going to walk through setting up your first Amazon Aurora database cluster. Aurora is a managed database service that's 100% compatible with the open source MySQL database, with enhancements for availability, performance, and scalability. We'll see how each of these goals is addressed. Our Aurora cluster will consist of two database instances. One is the primary, which can handle both reads and writes. The other is a read-only replica. Let's get started. We'll log into the AWS console at console.aws.amazon.com and go to RDS under Database. As you can see, RDS stands for Relational Database Service. We'll check our instances and clusters, and we see that there are none. Go back to Instances and launch a database instance. You have a choice of which database engine you want to launch. We'll select Aurora. Aurora offers you a number of choices, and you can see the characteristics of each instance type. The performance characteristics of Aurora are much different from vanilla MySQL. So if you've been running MySQL somewhere else, like RDS MySQL, I suggest you first run a proof of concept with your workload to determine the right instance type for you. For this tutorial, we'll select T2 Medium, which is typically appropriate for a dev test environment. Next, we have to decide whether to operate in high availability mode with a read replica in a different availability zone, meaning a different location. We'll choose to have a read replica. We're not locked into what we just selected. If our database grows, we'll be able to scale it with bigger instances and more replicas, and then downgrade if we no longer need them. Then we choose a database name, which is stored in lowercase. We choose a master username, which must start with a letter, and set the password. We're just a few steps away from launching our Aurora cluster. For the purposes of this tutorial, we'll go with the defaults. A few notes. An Aurora cluster has to be part of a virtual private cloud, or VPC. The VPC helps you control access to your database cluster, but you can configure permissions so that EC2 instances and devices outside that VPC can reach the Aurora cluster. You can add an identifier for a database cluster. You can also create a database within the instance. Let's go with the name tutorial_DB. If you choose to enable encryption, you have to provide a key. You can decide the order in which you want to failover across your different replicas. This is helpful, for example, if you're running production databases on larger instances and replicas on smaller instances. In that case, you'll want to make sure your production database fails over to another instance of the same type. Finally, you can customize your maintenance window as needed. That's it. We're almost there. Remember that Aurora is a paid service, so you'll incur charges if you click Launch DB Instance. But let's go ahead and launch the DB instance. You'll see two new instances being created. This takes a few minutes as we provision the machines. Under the replication role column, you'll see that one of these instances is the writer and the other is the reader. We can see the names of the databases. We use the cluster endpoint to access our database from a MySQL client. As you can see, our database is publicly available. With that, our database is set up. We can now enter the cluster endpoint in your favorite MySQL client, connect, and fire away. Notice it's the same database names that we saw in the console. We've seen how Amazon Aurora makes it easy to set up a completely managed database cluster in the cloud with high performance and full MySQL compatibility. In other videos in this series, we'll learn administration topics like backups, replications, and migrations. If you have additional questions, refer to our online documentation at aws.amazon.com/rds/aurora/resources. Thanks for watching.
Welcome. We'll now learn details about the main features and benefits of Amazon DynamoDB. Amazon DynamoDB is a fast and flexible non-relational or NoSQL database service. It supports both the document and key value store models. Its benefits include the following features. First, because DynamoDB is a fully managed service, you can create a database table and set your target utilization for automatic scaling. As your application scales, DynamoDB automatically handles database management tasks such as hardware or software provisioning, setup and configuration, software patching, operating a distributed database cluster, and partitioning data over multiple instances. DynamoDB also provides point-in-time recovery, backup, and restore for all your tables. Secondly, DynamoDB provides low latency queries. The average service-side latency for running a query is typically single-digit milliseconds. DynamoDB uses automatic partitioning and solid-state drive technologies. This means that as your data volumes grow and application performance demands increase, DynamoDB can meet your throughput requirements and deliver low latencies at any scale. Third, DynamoDB integrates with AWS Identity and Access Management, or IAM, for fine-grained access control of the users in your organization. You can assign unique security credentials to each user and control each user's access to services and resources. Fourth, DynamoDB supports storing, querying, and updating data through JSON documents. This makes it ideal for storing semi-structured data and manipulating with JSON queries. Finally, DynamoDB integrates with Amazon CloudWatch so that you can get statistics on throughput and latency. DynamoDB stores data in tables, which contain items with attributes. You can think of items as rows in a relational database and attributes as columns. DynamoDB distributes data across multiple partitions. It divides data items into partitions based on the partition key value. A partition is an allocation of storage for a table. A partition is implemented in SSDs and is automatically replicated across multiple availability zones in an AWS region. DynamoDB handles partition management for you. The partition key of an item is also known as its hash attribute. You can also define a sort key so that all the items with the same partition key value are stored physically close together and ordered by sort key value in the partition. This structure creates a one-to-many relationship based on the partition key. It also enables querying on the sort key attribute. A table has a primary key that uniquely identifies each item in the table. There are two types of primary keys. First, there is the partition primary key. The primary key consists of a single attribute, which is the partition key. DynamoDB builds an unordered index on this primary key attribute. Each item in the table is uniquely identified by its partition key value. Secondly, you can also have a partition and sort primary key. This primary key is made of two attributes. The first attribute is the partition key attribute, and the second attribute is the sort key. DynamoDB builds an unordered index on the partition key and a sorted index on the sort key attribute. Each item in the table is uniquely identified by the combination of the two values. In the example, the table has a partition and sort primary key that consists of the attributes user ID and order ID. For information about the DynamoDB data model and tables, search for NoSQL design for DynamoDB in the AWS documentation. DynamoDB global tables provide high availability and scalability across regions. A global table is a collection of one or more DynamoDB tables that are owned by a single AWS account. The tables in the collection are known as replica tables. A replica table, or replica for short, is a single DynamoDB table that functions as a part of a global table. Each one stores the same set of data items. Any given global table can only have one replica table per region. Every replica has the same table name and the same primary key definition. When you create a global table, you specify the AWS regions where you want the table to be available. DynamoDB performs all the necessary tasks to create identical tables in these regions. DynamoDB also propagates ongoing data changes to all the tables. DynamoDB global tables work well for massively scaled applications that have globally dispersed users. In this environment, users expect very fast application performance, which they get by accessing the replica closest to them. If one of the AWS regions is temporarily unavailable, users could still access the same data in another region. Thanks for watching. See you in the next video. Welcome. We'll now review how to transfer data to an AWS database service. The services used are AWS Data Migration Service, which is also known as AWS DMS, and the AWS Schema Conversion Tool. AWS DMS helps you migrate databases to AWS quickly and securely. You can use it to migrate your data to and from most widely used commercial and open source databases, such as Oracle, PostgreSQL, MySQL, and Amazon Aurora. The service supports migrating databases to similar database engines. For example, from an Oracle database that runs on-premises to an Oracle database that is hosted in Amazon RDS. But you can also change the database engine during the migration. For example, you could migrate a database that runs on Microsoft SQL Server in your on-premises environment to a MySQL database that runs on Amazon Aurora. You can also use DMS to migrate your on-premises database to one that runs on an Amazon EC2 instance. Please note, DMS can migrate databases with no downtime. DMS also provides a schema conversion tool to help convert Oracle PL, SQL, and TSQL code to equivalent code in the Amazon Aurora MySQL dialect. When a code fragment cannot be automatically converted to the target language, DMS will clearly document all locations that require manual input from the application developer. You can use DMS for both one-time data migration into databases that are based in Amazon RDS and Amazon EC2, and also for continuous data replication. DMS will capture changes on the source database and apply them in a transactionally consistent way to the target. Continuous replication can be done from your data center to the databases in AWS. It can also be done in the reverse direction by replicating from a database in AWS to a database in your data center. Lastly, ongoing continuous replication can also be done between databases with either the same or different database engines. You can use DMS for many different migration scenarios. Just remember, one endpoint must always be located on an AWS service. You can't migrate from an on-premises database to another on-premises database. This table lists the supported source-target database combinations supported by AWS DMS. It's important to remember that one portion, either the target or the destination, must be on the AWS cloud. AWS DMS architecture consists of 4 components. The first component is the replication instance. This is an Amazon EC2 instance that runs the tasks that are required by the migration process. The replication instance, or replica, runs in a virtual private cloud, commonly known as a VPC, and performs the work of database replication. It is highly available because it's deployed across multiple availability zones. It is synchronously replicated across availability zones to a standby replica to provide data consistency and redundancy. Security is enabled through storage encryption. You can encrypt the storage with either a default key in your account's key management system or with your customer primary key. Secondly, the migration process is made up of tasks. Tasks run on the replication instance, and multiple tasks can run concurrently in the same instance. A task can be configured to migrate only existing data, migrate only ongoing changes, or both. The third component is the source. The source is the endpoint of the source database, which can be running on premises, on Amazon RDS, or on Amazon EC2. The final component is the target. The target is the endpoint of the target database on AWS. You migrate data with DMS by first creating a replication server. Then, you specify the source and the target endpoints that have connection information about your data stores. And finally, you create one or more tasks on the replication instance to migrate data between the source and target data stores. AWS DMS creates the target schema objects that are needed to perform the migration. However, DMS takes a minimalist approach. It creates only those objects that are required to efficiently migrate the data. It does not perform schema or code conversion. To convert a schema or code, you can use the AWS Schema Conversion tool, commonly known as AWS SCT. This tool helps automate the schema and code conversion tasks for a database or data warehouse migration. SCT enables you to convert your existing database schema from one database engine to another. It also supports application SQL conversion to handle any SQL coding changes that must be implemented as the result of the migration. SCT can be installed on Microsoft Windows, Mac OS, Fedora, and Ubuntu. It supports SSL connections to the source and target engines. In addition to converting databases schemas, data warehouse schemas, and SQL code, SCT includes a code browser for viewing any manual edits you must make. AWS SCT facilitates heterogeneous database migrations by automatically converting the source database schema and a majority of the database code objects, including views, stored procedures, and functions. It converts schemas and code objects to a format that's compatible with the target database. Any objects that cannot be automatically converted, such as database-specific scalar functions, are clearly marked. This way, you can manually convert the objects to complete the migration. The table here identifies the source and target databases that are supported by SCT. To download SCT for your platform of choice, search for SCT on the AWS homepage. To see the complete list of supported source and target database types, search for Schema Conversion Tool Targets in the AWS documentation. Thanks for watching. See you in the next video.
It's now time to recap the module and review a practice certification exam question. In this module, we learned about managed database service types offered by AWS. You now should be able to describe the capabilities and benefits of Amazon RDS, Amazon Aurora, and Amazon DynamoDB. You also learned about AWS DMS and the accompanying AWS SCT. Great work! Now, let's review a sample certification question. Take a minute to review a sample question. Review the sample scenario and note any keywords that will help you identify the correct answer. Here, the keywords in the scenario are highlighted. Now, consider the possible answers. Keeping the keywords in mind, think about the answer options and try to rule them out. The best solution here is to select Amazon Redshift. Now, it's time for you to complete the Module 6 Challenge Lab. Thanks for watching. We'll see you in the next video. Welcome to Module 7 of AWS Academy Cloud Operations. In this module, we will introduce you to networking on AWS. We will learn about the key networking components that are used in the AWS cloud, including a detailed look into a virtual private cloud, commonly known as a VPC. We will examine the networking components of a VPC, including subnets, route tables, and gateways. We will also learn about VPC connectivity options, security mechanisms, and guidelines for VPC troubleshooting. At the end of this module, you will be able to explain the foundational role of a VPC in AWS cloud networking. You will be able to identify and explain the networking components inside of a VPC. You will also be able to differentiate the options for VPC connectivity and describe the layered network defense model inside a VPC. Finally, you will be able to configure a VPC and lists the step to troubleshoot common VPC networking issues. After completing the videos and lab exercises, you will check